Hi, welcome to my channel, JaberTime. Today I'm going to go over functions, relations, tables, and equivalent expressions. A function is a relation for which each value from the set of the first components of the ordered pairs is associated with exactly one value from the set of the second components of the ordered pair. A relation is just a set of ordered pairs. Now, to explain those two conditions, I have to show you enough examples, and this is what I have for you. This graph right here shows a mapping or ordered pairs. 1 goes to 5 and 2 goes to 7. It's a function. Every input has exactly one output. This one right here, I know the arrows are kind of mixed, but still, it's a function because 1 has only one output, which is 5. And 2 has only one output, which is 7. It's the same one that we have before, except the 5 was written down and the 7 was written up. It's the same one. You could see that, right? Now, this one is not a function because 3 does not have an output. The first word that was highlighted or written in red, it says every. So 3 is an input or part of the first component, but it does not have an output. This one right here is not a function. Why? Because 1 has 2 outputs, as we could see, and it's not supposed to. It says in the definition exactly one output. So 1 has 2 outputs means no. This one right here, they share the line, but still, it's a yes. Every input has exactly one output. 5 has exactly one output. I'm not asking you or questioning what is the output. It's 9, I know that. But 6 doesn't have 2 arrows like the previous one. Look at this one. This one shows right here. I'm looking right here. I'm not looking right here. This right here shows that it has 2 outputs. Where in this one, 5 has one output, 6 has one output. So we're done. This one right here, it's a yes. Every input has exactly one output. The 5 is something else. That's for types of functions, but we're not considered to look at the 5. We are considered to look at the inputs, and they have to have each one of them exactly one output. This one here, they both go to 2, just like one of the previous examples, so it's fine. 4 has exactly one output. 5 has exactly one output. How about this one? It's a circle. What do you think? Well, to explain through graphs, we say that it's not a function because it does not pass the vertical line test. You could see a vertical line right here, crosses the graph at 2 locations. To explain more about the vertical line test, here's a graph. That's not a function. Vertical line test. Again. Not a function, does not pass the vertical line test. Look at, for example, if this is 0, 5, this is symmetrical below the x-axis, which is 0, negative 5. Differently, I could say that 0 is going to 5 and 0 is going to negative 5. 0 has 2 outputs, so it's not a function. This one right here, I'm giving you the answer for this function, but we're gonna work together to verify why it's 2x plus 8. Now, these tables, because this is the first video for functions and relations, I made the examples or the tables easy to follow. Because if this is 1, and this is 2, and this is 7, and this is 22, and this is 58, it's kind of like jumping around, which is a little bit harder to find what's going on. So let's start with simple examples. On the left, you're going down by 1. Or you're adding 1, by the way. From 1 to 2, you're adding 1. From 2 to 3, you're adding 1. So this is fixed. Now you go to the right side. If this is fixed, that's a good sign to start, and it's an easier problem to tell. To the right side, I could tell that the differences are 2 all the way. So it is fixed. Once you have it fixed from the first time, first difference is fixed, we call it linear. But not only that, you see this number 2? It's actually the slope too. So now we know the slope. We know it's linear because its first difference is fixed. And we know the slope. To find b, we could use any point. I'm going to use 3, 14, this one here in the middle. Put 3 for x, put 14 for y. That's a 6. Subtract 6 from both sides to leave b alone. So b is 8. Now it's 2x plus 8, which verifies this. To check, let's take 1 and 10. Plug in 1 here. 2 times 1. Add 8 to it. Is it 10 as they claim? Yes. So sometimes it's worth to check your answer, especially if it's a test or a quiz. And this is how you do it. Let's take another example. Now this one here is 5, 10, 15, 20, 25. Keep in mind, I'm just keeping this 1, 2, 3, 4 as fixed. Now these are fixed, which we saw earlier. To go from 5 to 10, you're adding 5. From 10 to 15, you're adding 5. From 15 to 20, 20 to 25, you're still adding 5s. So it is fixed. That means it's linear. That means the slope is 5. But I could see that it's just 5x. 5 times 5 is 25. 5 times 4 is 20. 5 times 3 is 15. So I don't have to look for b. I could just see it. It's a simple example. This one here. This is fixed or consistent with a fixed difference. This 2 to 6 to 12 to 20 to 30, it looks like it's increasing as we go. It's not fixed. Here's the work done for you, so I could save you some time. I don't want to make a video of 30 minutes if I could make it, let's say, 18. So the difference here from 2 to 6 is 4. From 6 to 12 is 6. And as you could see, it keeps increasing. Now do the difference again. From 4 to 6 it's 2. From 6 to 8 it's 2. From 8 to 10 it's 2. Now I have it fixed. It took me 2 steps to find the fixed difference. That means it's a second degree polynomial. And I'm giving you the answer. Because it's not our topic here to how to find ax squared plus bx plus c that fits this table. In other words, how to target and solve for a and b and c. In this case, a is 1, b is 1, and c is 0. By the way, you could double check. Let's check one of them. Let's take 5. 5 squared, 25, plus 5, 30. So that's the equation. Here's another example. Fixed right here, same difference. 2, 5, 10, 17, 26. Okay, let's investigate. I see the difference 3, then 5, from 5 to 10, and so on. It increases. But it takes me to another step to find the fixed difference, which is 2. That means it's a second degree equation, and I'm giving you the answer, x squared plus 1. Let's give it a try. 5 squared, 25, plus 1, 26. Another one, 4 squared, 16 plus 1, 17. Just to confirm that what we are doing is actually a second degree behavior. Here's another example. Is this a function? What do you think? Notice that I repeated the 3 here, right? The answer is yes. Because 3 is going to 3 and 4 is going to 3. They share the output, but that's not our topic. Our topic says every input has to have exactly one output. I could see 3 has only one output, and the 4 has only one output, so it's yes, it's a function. Another example. Let's take a look. They want to trick me here, right? You see the 3 here and the 3 here? See, my focus is here, mainly, for functions. 3 is going to 3 and 3 is going to 5. That is not a function. 3 has more than one output. Another example. Well, that is so clear. Take a look. 1, 1, 1, 1, 1. 1 has 1 as an output, 2 as an output, 3 as an output, and so on. 1 has more than one output, not a function. Another example. 1, 2, 3, 4, 3. 3 is repeating. So what's happening here? 3 is going to 2, 3 is going to 2. This is a tricky question. It's fine. It's just like they repeated that. It's a function. Every input has exactly one output. 3 has exactly one output, which is 2. For example, also 4 has exactly one output, which is 2. The exactly is still valid for every one of them. Now let's take different examples about expressions and equivalent functions. I have two expressions. This one is simplified. This one is not fully simplified or standard form. That's not the standard form. This is standard form. I want to determine if these two are equivalent. To do it, you do the algebra for the first one and you try to simplify it or put it in standard form to see if it agrees with this one. Let's take a look. Here's the first one. To multiply this by itself, I could use different methods. I could use distributive. I could use the FOIL method. I could use the box idea. Let's use the FOIL method for now. Using the FOIL, F for the front, O for out, I for in, and L for last. Look at the fronts. The front times the front, x times x, which is x to the second. Out, x times 4, that's the outer ones. That's x times 4, which is 4x. Look at the n. The n are inside. When I reach inside, a shortest distance between them. 4 times x, as you could see, which is 4x. Last, the last one times the last one, that's 4 times 4, which is 16. Now, put this together right here. I notice that these two are alike, so I need to combine them. This gave me 16, but originally I had a 6 right there. I don't want to ignore it. Those are like terms also. 4x and 4x is 8x, 16 and 6 is 22. And now I need to look because that is the final answer for the first equation or function. Then I say, yes, they are equivalent. I have the same terms. Another example. This way I'll go a little bit fast to save you some time. The top one is on the left and the bottom one is on the right. This way I'm using the box. X minus 5 to the second means x minus 5 times x minus 5. Here's the box method. X and minus 5 times x and minus 5. This is x squared. This would give me minus 5x. This will give me also minus 5x. And the last one will give me a positive 25. These two are alike. That's why I'm circling them. That will give me minus 10x. Don't forget the plus 6 at the end. Combine like terms. That's a 31. Done with the first one. Let's go to the second one. Here I'm using distributive. And here I'm using the box. X minus 1 times x minus 1. As you could see, it simplifies to minus 2x when you combine like terms. So this right here will give you x squared minus 2x minus 2 of them plus 1. And this right here, distributive, will give you 2 times 15, 30. And 2 times negative 4x is minus 8x down here in blue. Now, this and this are alike. Minus 2x and minus 8x is minus 10x. 1 and 30 are alike, which is 31. Now I need to look left and right to see, to compare. Yes, they are equivalent. Take another example. Now I have work here and work here, so distributive and box right here, let's say, or foil, whatever you want. I like the box. It's kind of like quick and easy to do. So the top one, do the box right here, multiply x plus 1 times x plus 1, as you could see. X plus 1 times x plus 1 gives me x squared and 2x and 1. Bring this down. Combine like terms. That's a 3x to the second, 1 and 2 more of the same x to the second. Bring the 2x down and the 1, and we're done with this function. Second function, 2x plus 1 times 2x plus 1 will do with the box. Distributive right here, don't forget the minus sign. Minus 2x times x is minus 2x squared, minus 2x times 1, which is minus 2x. Bring this down and combine like terms and bring it down. 4x squared, 4x and 1. Bring this down right here. Underline the like terms. These are alike. 4x squared minus 2x squared is 2x squared. 4x is and minus 2x. It's underlined in blue. I was supposed to box it in green. 4x and minus 2x is 2x right there. 1 by itself. They're almost identical, but they're not. If you look at the 3 here and the 2 here, we could say that they are not equivalent. They have to be exactly the same to be equivalent, of course. Here's another example. The first one on top is the one that we need to work on, and the second one, we will leave it. It's x squared plus 2. It's already simplified. X minus 3 times x plus 3 plus 11. Put this in green, and this is in blue. I'm going to work on these ones right here in the box. X minus 3 times x plus 3. That will give me x squared. That will give me minus 3x. And this one will give me 3x. Those are alike, but they will cancel. 3 times negative 3 will give me negative 9. Let's bring them down first. And bring the 11. Don't forget about the 11. These will cancel as we said. Now x squared minus 9 plus 11. These are alike. They need to be combined. Let's say it this way. 11 take away 9, which is 2. We're done with this one. Go back and compare it to the other one given to me. I would say they are equivalent. One more. The second one is already in standard form. The first one we need to work on it. And here's the work. Trying to save you some time from going step by step. So we have x minus 4 times x plus 2. X minus 4 times x plus 2. I have x squared here. I have minus 4x here. I have positive 2x here. Minus 4 times 2 is negative 8. Combining like terms, the minus 4x and 2x will give me minus 2x. Now, I have x squared minus 2x minus 8. X squared minus 2x minus 8. Of course, you need to bring this down. Now, these are aligned, or like terms, underlined, I mean. 6x squared and 1 more x squared will give me 7x squared. Minus 2x minus 8. Compare it to this one. Almost identical, but they're not. The minus 2x here, I have a positive 2x here, so I would say not equivalent. That should do it for now. Thank you for watching, and I'll see you in the next one. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.